the YouTube link is proper.
Yeah, because it's connected to the same stream. So I don't know why it's not going, because this new Zoom link, I've connected it to the main one. Yeah. See, it's going to the same one, but it's why is it not going live?
The embedded link, problem with the embedded link, the RTMP link that you have.
Yeah, it's going to my previous test link.
Saying live?
Yeah, but this is on my test link.
No, this is now.
No, but this is the link on which it should go live. Can you, okay, fine. Can you do this? Okay, just send this over here. Sorry about this, guys. I don't know what the hell is going on.
I think your WhatsApp is already open. No.
What's up with me?
Yeah. Richa is open over here. Where are you sending?
Yeah, to Vaibhav. Yeah, could you just copy that, what I've sent you, and just put it here?
Okay.
Are we live?
Yeah.
No, but then.
Anool, can you move? Can you come on screen?
No, 1 second. Vaibhav, why did you go back? What did you do? No, I don't want this. I want you to share it with the over there.
No, wait. Are you, Anool, are you on the main screen?
Yeah, I am.
Where are you sitting? Are you in front of the camera?
Yeah.
Okay, so we're seeing back something else over here.
Huh?
This is like back in time.
No, it's right now.
Oh. Okay, done. So new link. We're live on YouTube.
Okay.
New link though.
So everyone has to pay for. It keeps going up and down. So medium ही रखो. High मत करो.
हाँ, medium ही रखते हैं. And keep going.
Okay.
That's our notification.
Okay.
Okay, guys, I think we're live. I can see that on the link. Richa, everything good?
Yeah.
Okay. Have you shared the new link with everyone?
Yes, we have. Just give it 5 minutes. Everyone's moving to this one.
Okay, guys, I think we're live. I can see that on the link.
I can see Vijay on the screen.
Good. By the way, Richa, I could hear myself on YouTube.
So that's not.
I think from your side, so you'll have to make sure that that's muted or the sound is off, otherwise it's going to come in.
Okay, I'm just pinning in everyone. Okay, can everyone see us? Okay, there's some more people joining. All right, everyone. Thank you so much for joining in. Can everyone hear us, see us at the moment? We're just waiting for another 4 to 5 minutes for everyone to switch from the other channel to this channel. These technical glitches are a little difficult to handle last moment, so sorry about that. Okay, so I think most people are back on. So let me just start the session finally. Hi, everyone. My name is Richa. I'm part of the Makers Asylum team. And thank you so much for being patient this Sunday evening to join us for this webinar on how to make oxygen concentrators. So just to give you a quick brief into what we will be doing today and what will the agenda look like. So just a quick context about the M19 initiative and the collective. Makers Asylum is a community makerspace we started back in 2013 out of a little garage in Mumbai to create a space for people to come together and make. So since 2013, we've been focusing around building the maker community across the country and working on various open projects where people could contribute openly, share knowledge, and rapidly scale solutions. So last year, we started something called the M19 initiative. The thought of the initiative was to support the frontline workers for COVID relief. And we started with basic things around designing a face shield. And incidentally, obviously, it was just the 3 of us in our team that were quarantining at the lab, and we started making it. And we had a very modest goal about making 1,000 of them. But unfortunately, 1,000 was a very small number when India went into the lockdown. And we started getting a lot of requests, and slowly, what we realized was it's important to open the design and activate many more makers across the country who could come and collaborate and create more. So in about 49 days, we were able to activate 42 cities, towns, and villages. A lot of makers, a lot of industries, a lot of different kinds of folks joined the collective, and we were able to make 1 million of them in 49 days, which was very agile and decentralized way of sort of functioning. And that's how the M19 initiative started back in 2020. And then in December this year, we started researching about the oxygen problem. So while we made face shields, the collective as a whole also worked on various things like active respirators, sanitizers, baby face shields, superhero shields, a rebreather mask for senior citizens. So a lot of really exciting new products that the collective has been working around for over the year. And in December, we were researching about the oxygen problem because we were anticipating that there could be a potential problem in India. And that's when we realized that there was an open source design and we could possibly, sort of recreate it in India using local parts. But in December, the situation was very different. And we decided to, lay low on the research. But in April, again, with the entire focus around oxygen and the oxygen problem in India, the collective sort of started coming back together to work on this oxygen problem in an open fashion. And that's when we started to work on the oxygen concentrators. So in the last 45 days, approximately, we've been working across 17 states, but largely we have about 20 to 25 advanced prototypes, which are now working at between 15 to 20 liters per minute and 95% oxygen concentration levels. So which is supposed to be useful for ICUs and can be put in high risk environments as well. So that's where we are at. And today the entire collective, not the entire collective, because the collective is about 600 people, but some really key members of the collective have joined in to give you an insight into the open work that has been happening. And it's just been really beautiful to really see so many people collaborate together to share knowledge with each other and actually accelerate the whole process of the development of the oxygen concentrators using locally available materials, locally available parts, and how to acclimatize it to Indian weather, because a lot of concentrators that we're getting in the market are all also getting bad very quickly because of humidity. There's a large humidity issue in India. So the collective has been tackling various pieces of this puzzle, and we do have about 2 units which are on the engineering certification level at the moment, and we are hoping to have those certificates in, because while of course oxygen is one of the problems that the collective is solving, but we are also working on multiple other problem statements as a large open innovation ecosystem, where a lot of minds have gotten together to make this crisis and the pandemic a little bit more easier for everyone else. So there are a lot of projects that we're working on which are now going to be in the rural areas. There are different projects that we're working on which could be which are not only just oxygen based projects, but today we're going to be talking about the oxygen concentrators, how possibly you can make it as well. So it's a short demo, and then the collective and the members of the collective are also going to talk about specific problem statements that we tackled as part of the whole problem, and take the conversation from there. I hope you all are excited about it. And let me just introduce everyone really quickly so that, all of you can, say hi to them. So just bringing on Vaibhav and Anool, you want to say hi?
Hi, folks.
Hey guys, hey, really excited to show you guys what we have over here, but thank you, Richa, for the introduction.
Hi, so that's Vaibhav and Anool. They're joining in from Goa from the Makers Asylum team. Then we have Vijay. Vijay, you're joining in from Bangalore. He's the founder of Fracktal Works. Vijay, you want to say hi?
Hi guys, I'm really excited to be here and looking forward to interacting with all of you.
Awesome. Then he's joining in from Bangalore. Then we have Gorba, who's in Bombay. He's the founder of Paravai Lab. So Gorba, you want to say hi to everyone?
Gorba is on mute.
Gorba is on mute.
Sorry, guys. Hello, everyone. Nice to be here today.
Okay, great. And then we have Mohammed and Vivian, who are joining us from Dubai. And they've been working in this really exciting small setup from home and on the electronics part of it. So Mohammed, Vivian, you guys want to say hi?
Hi. Hi.
Okay,
I'm
great.
Vivian, and Mohammed is with the screens behind him.
Okay, amazing. And then last but not the least, we've got Krishna, who's joining us from Chennai. His lab is the Dverse Innovation Labs, and he's the founder of Dverse Innovation. And they've been doing some fantastic work in Chennai. So Krishna, you want to say hi to everyone?
Yeah. Hi, guys. Yeah.
Okay, great. So that's the collective, and hope you all are really excited about what we're going to show you. So the first piece of the puzzle is we're going to give you a demo into the system itself, and then go into respective problem solving that all the members of the collective have been working on. So I'm going to pass on the screen to Anool and Vaibhav, who are joining in from Goa. So Anool and Vaibhav, over to you guys.
Thank you, Richa.
Thank you, Richa, for the introduction. Hey, everyone. Thank you all for joining in. Like Richa beautifully talked about how this collective works and everything. So we wanted to show you as to what we've been working on over here in Goa, the oxygen concentrators, and give you a basic rundown of how they work. But at the same time, we wanted to stress a lot on the open innovation angle of this and how all the labs across the world have collaborated, different parts of the country, to be able to quickly, rapidly, not just innovate and make these, but at the same time, really understand what are the problems that are local to India and how do you climatize these oxygen concentrators to be able to work efficiently and perform better in our country. So it's a big collective problem solving that happened over the past 45 days. I'm pretty excited to show you guys some of our results and everyone's results because I think it's been beautiful. So
first off, let's switch on the machine.
So what we'll do is I'll just give you a rundown of how this machine works and then turn it on and explain more. So the way the machine works is there are three parts of the machine which are critical. Number one, the compressor unit. So the part that you can see over here at the bottom, that's where the compressors sit. That's where air delivery comes. I will also open this on my phone so that Richa can print both the screens for us. Yeah. So what you see over here at the bottom is the compressor module. That's where you're getting the air into the system. Next, you have certain cooling coils that are able to cool this air coming out of the system. The next key important part of the system is the moisture separation part, because when we talk about it, in India, the moisture level at the moment is 94.9%.
Yeah. So next up is most of the moisture gets trapped over here in the moisture separator, and we have a
Desiccant chamber
here.
The desiccant chamber is something like Silica Gel that basically helps take off as much of the alumina zeolite is what we're using, but similar to Silica Gel. Just to give you a thought process, it looks something like this. Inside this, that helps take the humidity down further from 90% with the moisture separator and this down to about 5 to 10%.
So we have 90% here. After the moisture separation, we have about 40%, 30 to 40%. And after the desiccant, we have about less than 15 or 10% moisture.
Once it leaves from here, it gets into the system where it goes into the oxygen generation part. The way the oxygen is really generated is that once you have this pressurized air, it sort of gets in using a valve, which I can show you at the back, into the sieves. And what these sieves are really doing is they're filled with this chemical called zeolite. And what they do is they stop the oxygen from going up and push the nitrogen down by absorbing it. And what gets released on the top, in very simple words, is oxygen. And the nitrogen is then pushed down. So because the nitrogen is being pushed down, there is a requirement of a pressure swing absorption method in a case like this. And hence we have two sieves over there. So while one of them is charging up and releasing oxygen, the other one is actually throwing away the nitrogen from the bottom where it's entering into the sieves. So when I turn the system on, so what you'll hear is that one of them is pumping up and the other one is pumping down. While the other one gets pumping up, the first one goes releasing nitrogen. So one at a time, they release oxygen and nitrogen, right?
Yeah.
On the top of the system is all the electronics, so sort of like the brains of the system, which is powered by an Arduino and a bunch of relays that is controlling the motion between the left sieve and the right sieve. That comes in the air from, the oxygen from the sieves goes into this tank over here, which we call a surge tank. So this basically helps us hold the oxygen at the right pressure so as to reach 10 to 15 lpm. So it sort of acts like a buffer area where the oxygen is holding. And then from there, we get into a pressure regulator where we're able to regulate how much air is going in and out. And You have an oxygen sensor to basically measure out. You have an oxygen sensor to possibly measure out the exact amount of oxygen that you're getting out. So that's pretty much all of the system.
Goes into the flow meter.
Yes. This part goes into the flow meter that you can see over here, and where you can actually see exactly how much LPM is the flow. Obviously, right now the system is off. Anything that you want to add?
Yeah, so the key to the whole system is the zeolite. Zeolites have the property where they absorb certain gases and don't absorb certain gases. And the absorption is more of a physical process that requires some pressure, for example. So the zeolite that we use, it's called, there are different versions, but you can use things like sodium 13X, or you can use lithium X, for example. And when you pass air, which is roughly 80% nitrogen and 20% oxygen, when you pass that air through a chamber consisting of zeolite, the nitrogen sticks to the granules of the zeolite, whereas the oxygen kind of passes through. And that's the basis of the whole pressure swing absorption process. So you have zeolite, you pressurize it, and nitrogen sticks to the zeolite. The oxygen passes through, you collect that oxygen as an outlet, and the nitrogen that is stuck in the zeolite, you kind of push it back out through a reverse pressure. So that is more or less the heart of the pressure swing absorption technique. It's not new, it's a fairly old technique, so it's been around for quite a long time. So that's the heart of the whole system. And then there are a couple of other important things that you need to take care of. Things like what's the pressure at which you're inputting air to the system, how much is the liters per minute of air you're putting in, and your output directly depends on that. So the more input you have, the more output you get, for example. Ambient temperature plays a big part in your system's performance. Ambient humidity is equally important. So the last 45 days, these are the challenges that we've been tackling. I'm trying to figure out what affects the system, what makes it better, what makes it worse, and so on. And based on that, we built a couple of prototypes. That's the first one that we had is, I think Vaibhav can probably show you.
You can talk about that.
So this is the first kind of system we made. It's kind of disassembled at the moment, but this was based on design known as the Oxygen. For several reasons, of course, we decided to move away from this design and make some improvements, which led us to this second version over here, which is what we see here. And based on what we have learned with this system, is version 3 that we have just kind of finished. Still needs some wiring up and so on, but it's pretty much assembled at this moment. Just needs the electronics to go in, and we should be able to test it out within some time. Two of the biggest challenges we faced was how to get the required amount of oxygen at the high flow rate that was required. So for COVID patients, you need anything up to 15 liters per minute at a concentration that is 93% plus or minus 2 or 3%. So nothing less than 90% is what your expectation is from the machine. And getting that is a bit tricky in many engineering ways. So we can. So first off was when we did the version 1, we were using a zeolite known as Sodium 13X. A lot of different labs have tried the same zeolite, and performance was a bit tricky in India with the high humidity we have. That's been a big killer for the zeolite. The trouble with humidity is zeolite absorbs moisture or water better than nitrogen. So after some time, the performance of the system really degrades quite a lot. So most of the labs, some of the others who are here today will walk you through their trials about having worked with sodium 39. But after about a month of trying out sodium, we came to the conclusion that we need a better zeolite. And our current choice is Lithium X. It's a much more efficient material. It is 3 times better than Sodium X, so we get better performance. We can make a smaller system. It's more compact. And also some of the other elements that are required in the sodium system are not required in the lithium unit. So there is a kind of a cost balance in that too as well.
Want to show this?
So yeah, quickly, this is what the current version 3 schematic looks like. It's quite simplified. There's really not a lot to it. We have a compressor, we have some cooling coils, and we have a moisture separator. And at the end of that, we measure the humidity. And we have an alarm over here. If the humidity increases above a certain level, we can go on and kind of shut off the system so it doesn't damage the zeolite. The compressor then goes into a valve which is connected to the 2 sieves, sieve A and sieve B. And that's how the swing takes place. The pressure swing is adsorption.
Can you mute that?
So, pressurized sieve A. And while sieve A is being pressurized, sieve B is venting out to atmosphere whatever nitrogen it has collected. During that time, sieve A is collecting nitrogen into the zeolite, but allowing oxygen to pass through and come out through the orifices into the search tank. And then after a certain amount of time, which is based on the timing cycle set in the electronics, you flip the thing over, and your sieve B starts charging with air, pushing oxygen out and holding nitrogen here. And sieve A starts releasing nitrogen that is captured in the previous cycle. And this kind of cycle keeps going back and forth, swinging from sieve A to sieve B. So the output of the 2 sieve tanks then goes through a valve into the search tank, which is kind of a buffer tank to kind of even out the fluctuations in the output delivery. And from there, basically, is where you get your pure oxygen. We have a tap off to measure the oxygen through the sensor. We have a pressure regulator to set how much air pressure you get at the outlet. You have a filter to make sure that the oxygen is filtered. And finally, there's a humidifier that sort of makes sure that the oxygen output is has some humidity, because you can't apply dry oxygen to patients, for example.
Now let's see it in action. And now what are we doing next is turning on the compressor, so it's going to be a little loud, but here we go. At the floor, as you can see, rising. So currently, it's at about 15 RPM. 15 RPM over there. This is auger based flow meter, so whatever you see, multiply that by 1.25. And then over here, what you see is the oxygen concentration. Which gets ready. We will see it flying. Okay. Turning that off so we can speak a little bit more. First big problem is about the zeolite itself. Sodium versus lithium. So lithium absorbs about 22 liters per minute. Ml per minute of nitrogen compared to sodium base, which only absorbs about 8 liters per minute. So it's 3 times more efficient, and that's one of the things that we've changed. Correct. You don't need the entire halo and a few other things that are there in a sodium-based system to optimize it. You don't need any of those things. So lithium ends up working as a much better option and is more commonly used in all the commercial oxygen concentrators in the world.
Second problem is that's a big problem for us, especially in India.
Yeah. So one of the systems that we tried out to solve humidity was this one that we showed you. The next system that we're testing out that Gorbachev can talk a little bit more about is chiller. So this over here, if you see, this is the chiller that we rigged up that acts. So there's a compressor. That's the heat exchanger. And that's the chiller. Yeah. So the output basically goes from here currently into our main system, directly into the big compressor, where the pipes can take it into our system. Okay, I think that's pretty much from our side. And now what we can do is let the other labs talk about their inputs. If anyone has any questions, they can reach out to us over the chat and we'll be able to help answer that, which I can take those questions for later. Hopefully we've explained this well. And Richa, can you take it forward?
Hi, thank you so much, Vaibhav, Anool. That was really, hopefully it was exciting for everyone. There are a bunch of questions on the screen. Ritesh, would you like to mute these guys, please? Yeah, that'd be great. Okay, thanks. So yeah, I'm just going to go back to now introducing Gorba. Gorba is, he's been working with us now. I mean, we now know him for about 45 days to about I don't know, about 2 months now, but he's been with us working on the concentrators in Bombay out of his lab. And we really miss Bombay because we recently moved to Goa. So he's just like our point of connect to Bombay again, because things get really done very quickly in Bombay and Goa. We have to keep waiting for a lot of parts as well. And of course, apart from being part of the collective, he is been working on various things, which I think, Gorba, you can also give a quick introduction about yourself to everyone. So I'm just going to pass on the stage to Gorba. He's going to talk about a few of the problem statements that he's been dealing with and show you a little bit about his prototype as well. So over to you, Gorba.
Sure. Hey guys, so nice to be here with you all today. So when we started 45 days back, you might all remember that there was a lockdown in various parts of the country, right? So it was very difficult to source various components which were like critical for building these oxygen concentrators, right? So one of them was a zeolite, and the other big thing is, where do you put the zeolite? The chamber where these molecular sieves would go in. So to begin with, like many other open source project and contributors across the globe, we started with these UPVCs, PVC pipes, Schedule 40 pipes, which are rated for high pressure, but there was a problem with them that the way everything has to be assembled took a lot of effort in terms of making sure it's airtight and the solvent has been cured overnight or like for at least like 6 hours, so that there's no leakage and all that. And there was also this problem of actually getting the right UPC scheduled type pipes, because you could get any other PVC pipe as well. So there was those challenging times because of the logistic part. So I'll just show you guys what pipes I'm talking about. So these are the pipes. Initially, when we started with this project, we were intending of using as the Maker Asylum folks, Vijay, Vaibhav and Anool showed you guys. The first prototype were built with these pipes. So these are standard end caps, and what we have is the 3x8 10 mm pneumatic connector. So we started with these pipes. It was very difficult to procure initially, but the problem was the leakage. So over the time, there were like micro leakages which used to happen, which is to degrade the performance of the overall system. So that was one challenge we had to deal with. So before we move forward, so the way to figure out how, if there is a leakage, you basically use something like this, a spray system, but you put shampoo or some kind of a soap in it. So you basically figure out if there is any leakage in any of the joints. You can figure that out using a shampoo and a spray. So so this basically works for making oxygen. The only problem is this: they need to be like well constructed and well assembled, and you should know what solvent to be used. So there are different brands of these pipes. This one is Prince. You get Astral and other brands. So you'll have to make sure the connector, the caps you get, the solvent you get is of the same brand. If you don't get it of the same brand, there might be some tolerance mismatch and leakage problems and so on. So so they work, but they were a challenge to build to start with. So after this, we moved to the aluminum cylinders, basically. Standard aluminum, like 2.5 inch ID and 3 inch OD auto diameter pipes. And we built this custom caps. These were like made using lathe. These are like threaded caps. So basically, these are like cylinders. You just have threaded caps at the end, and you just put them together, and you can fill your zeolite inside them, and which would act as the zeolite sieve, molecular sieve, and then you can basically push air via this end, and oxygen would come out of this end. But this had a problem again. I mean, these threaded caps were like difficult to put them on and removed for maintenance and other purposes. And there were like at times leakages as well because of the O-ring mismatch inside this particular cap. So so we had to come up with some other design. So for that, we basically came up with something like this. So basically, this can be welded on any aluminum pipe, like aluminum welding. And then there is this O-ring, which would go over here. And then you can basically clamp them together with 4 M8 screws. So this is what I'm using right now. I'll show you. This is a pretty reliable, easy for maintenance. Just remove the screws, refill your zeolite, or whatever you want to do with your zeolite, you can do that. So these were like the 2 approaches that we went on during the lockdown time, when there was a shortage of material and shortage of everything, right? So we did try this. They had good results. But in future, we might go with some aluminum extrusion, which are specifically designed for this purpose. They are called Mickey Mouse extrusions. Basically, they have these 4 years where you can clamp like a cap or something like that, and then it works basically as a cylinder, right? So that is for how you fill up zeolite into a cylinder. Okay. Before we move ahead, I just want to talk about zeolite. I know Vaibhav showed you guys a few the zeolite box and everything. So if you see the white granules, the fine particle that you see, that is the size of zeolite which you have to use. I mean, like they are like very small. If I can show you. So this is the zeolite grain at end here. It is 0.7 mm. So that is the fine zeolite granule that you need for generating oxygen. So there is 2 variants, as previously explained, there is the sodium and lithium-based zeolite. Sodium one, you need a larger volume for a particular liter per minute, and lithium one, you need a low volume for a particular liter per minute. So lithium is the preferred one, but again, we went with sodium and we had the results from the sodium zeolite. So I'll show you our current prototype, what we have. So this is our first prototype. You can see the sieve A, that is the sieve A over there, if you can see. The search tank in between, and then that's the sieve B. And this is our desiccator, where we have activated alumina filled in, which basically does the job of reducing the humidity level in the air system. So making sure that your air is dry is very essential. If it is not, then basically instead of absorbing nitrogen, you would be absorbing water, the zeolite, the sodium zeolite in these sieve beds will be absorbing water. So that should not be happening. So you basically use a desiccator, which is filled inside this particular chamber, which basically removes the moisture, and then it's sent to the other two sieve beds. So this one right now is each has like 1.5 kg, 1.5 kg of zeolite for like 12 to 15, 14 liter per minute. But if you want a higher liter per minute, you can actually increase the number of sieve beds, or you can use increase the diameter of your chamber. So this, if you can see, is the big radiator or condenser, whatever you want to call it, at the bottom there, which basically does the job of the cooling the air coming out of the compressor. The air that comes out of the compressor is hot. It's hot because of the piston head. So that needs to be. So it's in a vapor state. Kind of, the water is in a vapor state. The condenser helps reduce the vapor to cool down into water form, so that then that can be basically removed using a moisture separator. So this is a moisture separator here. I mean, it has a solenoid valve. So once the moisture reaches a particular level, we can basically remove the moisture from the airline system. So for medical air purpose, making sure the moisture is removed is very essential. So, so what we also have is something similar like other makers. We built a chamber. It has a sensor inside it. So the airline which comes from, if I can show you, yeah, the airline which comes from the top goes into that particular sensor, where we measure the temperature of the air and the humidity level of the air. Once that is measured, we know it is safe. Then it is sent to the sieve chamber A and B, and then that's where the oxygen is produced. So that's with the demo, and I explained to you guys about the zeolite. Zeolite, yeah, that's it. So other important thing that Anool talked to you guys about was the refrigerant system that the Maker Asylum guys have put together. We are building one as well, but that is in pipeline. But what it does is it makes sure the temperature of the compressor doesn't reach to an unacceptable level, because the air intake is already cooled. So the temperature of the compressor stays cool, and also you're making sure that that water is in a condensed form and not in vapor form. So that's where the refrigerant system for cooling air makes a lot of sense. And that's what even we are planning to put all together, and then we will be running the system. So that's with our prototype. Do I have anything else to show? Yeah, these are some RO canisters which a few people used. I mean, they gave results for some makers, but some makers had problems in terms of getting the right concentration. So there are RO cans, there are PVC cans which are made for this particular purpose, and there are aluminum cans. Okay, I got this sieve especially to make you guys to explain how an zeolite sieve works. So this is a steel sieve. So basically, it's what we use at home for basically like filtering out any dust particles from rice or wheat or anything like that, right? So what do? You put stuff, it gets whatever is required gets filtered out, and whatever is required stays up. So the same principle with zeolite. For oxygen concentration, what happens is these zeolites have these crystalline structure, which are specifically designed for nitrogen in medical for the oxygen concentration purpose. So these nitrogen molecules gets trapped in these crystalline micro holes, micropores, and then they are restricted from flowing up. So when the purge wall basically opens, so right now we are using a 3x2 wall. So when the wall opens after a particular cycle of absorption, these nitrogen are purged out. So that's how a molecular sieve works. Basically, this is steel sieve, and what you have inside an oxygen plant or oxygen concentrator, oxygen generator, a molecular sieve, because they work on a molecular level for filtering out nitrogen. So I think my time is up, and I think this is all this is all there is about oxygen concentration. I'm just going to try and just quickly show you a quick yeah, a quick GIF or what you can say as an animation, right? So this is a portable concentrator's flow. If you can see the air compressor, the motor sucking in the air from atmosphere, and then it goes into a heat exchanger because the water is in a vapor state. It needs to be condensed so that it can basically it can be removed. And then it goes to these sieve tanks where with the help of a wall you switch between sieve A or sieve B or whatever you want to call it. And then it goes to a surge tank where then it is pressure regulated, and it goes to the patient for use. So if you see, this is the traditional or the conventional oxygen concentrator flow. There are certain problems with this flow because these oxygen concentrators which are available in the market are not designed for what do you say, the our climate. Yes, it is. You can use it in our climate, as in if you are up north near the middle of India, like Delhi, for example. But if you're in the coastal region, this will mostly will fail because the option to remove moisture or the option to further cool it down are not scaled or are not climatized to our Indian atmosphere. So that's what we are trying to fix. We are trying to fix this part. We know this part, how it works and everything else. What we are trying to fix is this heat exchanger part and the optimizing it right now. So that is the challenge we have, and that's what you're working on. I hope you guys, whatever I said made sense, and it helped you in whatever you guys want to do with it. Thank you.
Thanks, Gorba. I'm going to then call upon actually now Vijay. So thank you so much, Gorba, for explaining how we were working on the sieves, the humidity issue. There are multiple pieces of this concentrator that we all, did not know about, but were able to sort of really discover as to what is the real functionality of it, what needs to be broken down. There are a lot of questions coming up around certifications and all of that. We will be answering all of that at the end of the session. There, I do understand that everybody has curiosities about, how will we get certified, et cetera. But interesting thing before actually Vijay goes into his presentation is that a lot of concentrators that are coming in are recreationally certified. So really, I mean, there's a question to sort of ask overall when you're buying and donating these oxygen concentrators, what are we really doing? But moving on, Vijay is like I mentioned earlier, he's the CEO for Fracktal Works. He's the founder there. He's been part of the hardware ecosystem for a very long time. He's been building 3D printers in India for about 8 years now. And he was with us in Goa since the beginning of the whole restarting of the initiative. He spent about 2 to 3 weeks, 2 weeks with us Oh, 1 week, 2 weeks with us.
1 whole month almost.
Oh, 1 whole month almost, actually, before he went back to Bangalore. And he will show you what he did after all the research that we all did together in Goa. And he will talk about specifically around something that we really designed for fine-tuning these oxygen concentrators, because we had multiple of these in different parts of the country. So we needed something to, also help people fine-tune the concentrators better for better output. So Vijay is going to talk about that. So over to you, Vijay.
Trying to figure out this dual screen thing. So I'll go to switch over to my phone so that I can move around, and I'll switch over the audio to.
Okay. So let me switch to forward. Okay, I can see this. So this is the oxygen concentrator that we've built. It's a little bigger, so this is based on the Sodium 13X. And because of that, everything had to be much larger than what Gorba and what the Maker Asylum team have shown. Let me see if I can switch to my front camera. Hold on. Oh, there you go. Much better. So so this is again, right now I'm using it also as my table, just to show you the live demo afterwards. So we have the display over here, which shows the oxygen percentage, all the critical pressures over here, and then we have the flow meter at the output. So this button primarily starts the compressor. So you make sure that the electronic starts before the compressor starts. I have the side open over here, so we have a 2.5 horsepower compressor, courtesy Maker Asylum for donating this for the time being. So this guy again is what is required for getting about 15 to 20 liters per minute from a Sodium 13X system. Right now I'm using Sodium 13X, and like Anool had mentioned earlier, again it compared to lithium, again it's 3 times less efficient than Lithium X. So to sort of compensate for that, you had to have a much larger compressor. And more or less, again, everybody's talked about the different parts. We have a much larger cooling coil. We have a moisture separator. More or less everything else standard. We have the halo, so we had to sort of have all of these components on it to make sure that you get 15 liters per minute from a Sodium 13X system. So I'm going to turn it on now, and I will show you the output. So turning it on over here, it might increase in volume. Yeah, so I'm going to switch over to my laptop now and show you LabVIEW, which we've been using to calibrate the timing parameters. Give me a minute.
Hello, can you hear me? Okay, Richa is okay. Awesome.
Yeah, go on, okay.
Yeah, awesome. So the device is on right now. I'm going to share my screen. Could you let me share my screen so I can show them the LabVIEW display?
You can now share your screen.
Okay, so a little backstory behind. I think I don't know. A little backstory behind this. So when we were at Maker Asylum, again there were quite a lot of problems to deal with. We were dealing with a cyclone. We were dealing with power outages, in addition to figuring out the oxygen concentrator. And this was the first time we were making it, right? And there are a lot of things that change when it comes down to when you're changing, the your ambient temperature, the size of the zeolite, the kind of zeolite that you're using. So we were not really understanding, what was happening by just using an Arduino. We wanted to see the cause and effect when you change the timing cycles in real time, what happens at the output, and also control it and try to understand, what changes in the system. So again, the three main timing parameters, if you can see my screen, again, the three main timing parameters on a oxygen concentrator. So you have your sieve, charge, and purge, where one sieve is generating oxygen and one is purging. You have your flush cycle, where all the oxygen being generated from one or most of it is being used to flush the other one and remove all the nitrogen. Then you have your pre-charge, where both the sieves are generating oxygen. So these cycles are extremely critical to figure out and fine tune, because ultimately this is what gets your high level of oxygen purity, as well as make sure that your zeolite lasts for a long time. Your zeolite gets saturated with nitrogen and it's very difficult to get started again. So I will start up my system. So I have it connected to the machine right now. I will turn it on. Okay. Okay, awesome. So now basically what it's doing is the compressor is off, so it's showing me the oxygen value at ambient. All of this can be calibrated from the settings. So this is what it's showing me is the timing cycles for my sieves A, B, and equalization, and I can change this on the fly over here, and it's giving me the oxygen value. So I will turn on the machine now, and then you will see how sort of the oxygen will start increasing. Slowly the oxygen is increasing over here. You can see right here. I also correspondingly showing the millivolt value. So slowly, it's sort of, it's not as responsive as lithium is. Sodium sort of takes about a minute or so to start getting it at 90-95. Yeah, there you and also, let me just show you this other screen. If you can see the other screen, the flow control valve, and it's showing. This is what we use to calibrate the machine. By changing these timing parameters on the fly, it's changing the, say if I make this say 500, then again slowly the oxygen value sort of goes up and down depending on these parameters. So that's how sort of we've been working on calibrating these machine, fine tuning the operating parameters. Again, okay, fine, now that I'll turn off the system. So we have not only been able to tune our machine, but quite a lot of other makers have been able to use LabVIEW to fine tune the process parameters for their machines. So that's been really cool. So yeah, that is the update from me, Vijay from Fractalworks. Hope you all are successful in building your own oxygen concentrators. Thank you.
Thanks, Vijay. Could you also stop sharing your screen, maybe?
Yeah, my bad.
Sorry.
All right.
Thanks so much, Vijay. I wanted to sort of really emphasize at this point that, sorry, one second, I'm just going to remove the spotlight. Yeah, so I was trying to sort of emphasize at this point that, yeah, there are a couple of questions that I wanted to take before we go to the next session with Vivian and, Mohammed. And so Gorba obviously explained a little bit about the sieve. There's some people asking us about the fact that why lithium versus sodium zeolite, right? And that's one of the questions that everyone's asking. There are, at least from what I understand, just to moderate this, is that lithium-based zeolite is more effective in absorbing the nitrogen concentration in air, and you require lesser amounts of lithium zeolite for better efficiency. Sodium but it is very expensive it's at least 3 to 4 times more expensive than sodium zeolite. Now, sodium zeolite, you will need more of it and has lesser absorption capacity. So hence your system will be a little bit more bulky. With lithium, you're able to sort of make a system which is a little, more compact because you're using lesser of it. So they have pros and cons. But zeolite in general, even if you use sodium or lithium, can, you will require to handle it really well because of the humidity and the temperature in India, because they get short pretty quickly if if it's not handled well. So it's only from a perspective of sort of the size of the end output that you need versus the, cost benefit analysis between these two. But effectively, both can do the same job. But most of us were having issues with sodium because we were not able to reach 90-95% concentration levels on the sodium. Hence, most of us decided to switch to lithium, which was giving us better output and much more efficiency. So I think that's one question I wanted to answer before I go to Vivian and Mohammed's presentation. And just to also emphasize the point that all of us are literally working in different parts of the country and literally working virtually. And as you progress into this entire webinar, you'll be able to see so many people have created their own concentrators. And this is with digital learning and knowledge sharing that we do. As we went along, as we all learned, we all shared with each other, and that's how the collective has been, working. So it's really very beautiful, how everything has come together and how much, literally having a product cycle of 45 days or a month is like unheard of. And being part of this larger collaborative community really allows you to have that cycle versus, if one of us was doing this and did not share with each other, I'm sure we would have taken 6 months or more to make an oxygen concentrator versus, sort of having a really open community that's sharing with each other. So just wanted to highlight that before I go to Vivian and Mohammed. And Vivian and Mohammed have been joining us from Dubai, and they've been working on the electronics and the PCB component of the oxygen concentrator. And I'm going to pass it on to both of them to really tell us what have they been up to and how they've been, contributing to the collective. So over to you, Vivian and Mohammed. Thank you so much for joining. I'm just going to pass on the floor to you.
Thank you very much, Richa. Hello, guys. My name is Vivian, and I represent Team Middle East. My friend Mohammed and me, we work in different industries, completely different environment, but we are avid makers. And when we heard about this collective, we wanted to be part of it. So that since we were working from Dubai, we couldn't actually do a lot of things to actually build the concentrator itself. So we were following the meetings and seeing the problems and trying to help out virtually. And what we realized was there was a lack of time for the people working in India to actually concentrate on the full printed circuit board to make it a full professional unit. So everybody has been doing the R&D on the mechanical side, the getting the concentrator working to achieve the 95% at 15 to 20 LPM. So I spoke to the guys over there, and then we decided to help out by taking the load off them to do the design for the board and to prepare the prototype and do the testing. So I'm just gonna move my camera a little bit to show you the prototype board that we have created already. This board, we received it actually yesterday from the PCB manufacturer in China, and we assembled it ourselves, all the components and everything. And I will just run through what are the main components that we have incorporated with this. Okay, the board is based on the ESP32 room module. which is over here. It's an SoC. So we have not taken the one with the built-in antenna. So since this unit would be mounted inside a case, so an external antenna can be mounted, which can be used for web-based settings or upload of new firmware or anything. Okay, this whole board is having 4 solid-state relays. Now each of those relay is a 1 amp solid-state relay, and we have 4 outputs over here, which is 3 for the solenoids, 1 for the fan, and 1 for the compressor. Now the compressor, definitely it's got a higher current rating. So this output is basically to run a contactor to connect the compressor. And over here we have 2 inputs. One input is for the on-off switch, and the other is for a high pressure break off for the compressor. In case the pressure in the line is higher than what is set, we need to break it off so that it doesn't create a problem in the unit itself. So the contact from the valve can be connected over here, and then the whole compressor can be shut down. The board works with from 12 volts up to 30 volts. We have a buck converter over here, and we have a 3.3 volt regulator. Apart from that, what we have also included, this connector over here is for a 2.2-inch SPI display, and this input is for the oxygen sensor. This is also included for any other type of oxygen sensors which could have an analog output. Then we have 2 I2C connectors over here and 1 UART connector. We have also included 1 more I2C for a pressure sensor, which is basically the BME 280 pressure sensor, which normally everybody uses. And we have also done a breakout for all the points over here. All the GPIOs are which are connected to the various devices are available here. This board could also be used for future purposes or using for any other applications as well, so that we have kept it generic and so that it can be used for any other future applications as well. Now, to actually do this whole board, as I told you, we designed the board over here. I'll just run through the board design. I'll share my screen. The whole design was done in Eagle Schematic, and that's the input power, the buck converter, and the 3.3 volt regulator. And each of the output has got 2 LEDs connected to it. Now these LEDs are connected in series to the SSR itself, so that in case the SSR is faulty, we will know. If the LED is not working, we will know that the SSR is faulty as well. Also, we have 1 LED across the output to ensure that the output is being powered correctly. This is for the 3 solenoids, and for the pressure switch, it is connected directly across the output, so that in case it breaks, your compressor is directly switched off. It's basically hardwired. Then we have a buzzer on board. We have the outputs over here, all the outputs for the 30-pin header. And we are using the CH340C. And that's the ESP32 module. That's the connections for the 2.2-inch TFT SPI. Then you have the I2C, and also I have also included 2 temperature sensors which can be wired in case you need to monitor temperatures and which is of the air which is coming out of the compressor and all that. It's available. And that's for the on-off switch. So reset circuitry and the outputs available, inputs and outputs available on the bus. So the board design, it's a 4-layer PCB. The size is 100 by 75. And we are still testing the board. At the moment, we have uploaded a Blink code, which was to test all the outputs. So I'm just going to connect the board so that that's what we have done so far. And apart from this, now we are working on the code itself. We have another member in our team, Mr. Mohammed Anas. He is working from Doha, Qatar. And Mohammed and I work in Dubai, and we coordinate, and we are doing the testing of the board and the code and any modifications to be done. Whereas Anas is working on an RTOS-based code for the entire thing, so that the cycles and various tasks which are to be done by the system, will be 100% right. We can make sure that it will be running correctly. So this code should be ready within this week, and we will be testing the board with that. And after this, whatever is the final one, the board will be shared in the group. Thank you, Richa. Mohammed, would you like to add something?
Mohammed, would you like to say something?
Actually, Vivian mentioned everything in details. That was beautiful. But I would love to answer 2 questions, which I would love to have more questions, but I got only 2 questions. First one was using Arduinos. Are they reliable? Actually, thousands and millions of other devices got either Arduino based, MPUs or STMs or ESP. So there's nothing more than that, and our application doesn't require something more than that. But we picked the ESP specifically to be able to do parallel operations at the same time. So to be able to use a real-time operating system. So real-time data logging and while doing other actions in parallel. And the second question was about the code. Would it be able to add, or the solution would be able to add other sensors? As Vivian discussed, you have all the GPIOs, or all the inputs and outputs of the microprocessor. They're all exposed. You can add whatever you want. But the main idea of the board is to standardize the code. The code and the board is like an open source solution. So the code with everyone, the board with everyone, and then we can discuss adding specifically what sensors, or maybe if someone wants to add some sensor that they cannot find in some places in India, then this discussion will be shared with everyone. I would love to hear more questions, and let's move.
Thanks, Mohammed. Awesome. So that's the team that's been working. Again, everyone's working in different parts of the world as well to get things going. And what I'm gonna call upon next is, one second, I'm just gonna, sorry. So I'm gonna call upon Krishna next, who is going to be joining us from Chennai, And of course, there are a bunch of other questions that we will be answering in the next, once Krishna is done with his presentation. He will be talking about how the collective has helped his lab, because they also started with us at the same time to work on things and build their concentrators in Chennai while there was a very strict lockdown that was going on in the last month in Chennai. So he's going to talk about specific things around how the collective really helped Dverse innovation in Chennai, and I'm going to pass on the floor to him. Krishna, up to you.
Sure. Thank you, Richa, for that. Yeah, hi guys. So this is Krishna from Dverse Labs from Chennai. So just to give you a brief background of what we do, we are a healthcare startup based in Chennai, and we design products for impact. So for the past 45 days, we've been associated with M19 Collective, and it's been quite an interesting journey because, like, as Richa was just telling, like when we started, we had a very strict lockdown and we couldn't really move, and we even had our own doubts of whether we can do it or not. So let me show you what we've been doing so far. I hope my camera is visible, Richa?
Yes, your camera is visible, Krishna.
Yeah, so this is the version 3 that we built. So we are getting around 80 to 82% at 10 LPM flow rate. And we have made quite some improvements from the previous versions, which I'll be sharing with you all shortly. So we are using 2 compressors. One is like a compressor head, and one we have like a compressor with a tank. So most of our condensation happens in the tank, and we also developed some low-cost methods to remove moisture, because since Chennai is also in a coastal region, we have issues with the ambient moisture being around 80% on an average. So yeah, So now let me share with you just a minute. Yeah, so now let me share with you how, the journey that we had so far.
Sorry, Krishna, could you share your screen again?
Okay, yeah, sure. It says screen sharing is disabled.
Yeah, you can try now.
Yeah, cool. Visible?
Yes.
Yeah, good. Okay, so those who are into product development will know that it's not a very quick and easy road to take, right? Like, I mean, product development itself takes a long time. So a few learnings from the past. Over the past year, we've been developing some automated sterilizers for elevators since the first wave, and basically we had underestimated the time and efforts to build a hardware product from scratch. So like we initially thought that it will take like a few weeks, but then it took like around 8 months to implement it in hospitals and start making impact. But then and also during the second wave, which was more dangerous, we were looking for ways to build oxygen concentrators, because as you know, like we had like a frantic need for oxygen supply, and many of our previous clients and hospitals, apartment residents, like were like kind of approaching us and asking if we can build oxygen concentrators for them. We wanted to help, but then we were also aware that we won't be able to do much alone, right? Because this time, added to the usual long product development cycle, oxygen concentrators seem to be even more complex with a life or death outcome, and also another other challenges like lockdown and how do we source materials, and taking forward the learnings from our previous experiences working as an active contributor in the open hardware domain. We wanted to join forces with the M19 Collective right from the start. And we felt that if we did it all by ourselves, we would have failed to develop a fully functional product on time. So we realized that the only possible solution is like an open innovation system, right? So so we joined the collective, and once the M1902 initiative was out in the social media handles, so many people were stepping in to help, either by sharing tools or resources, or and they were willing to build. But at the same time, it was also very dangerous to do that, right? Because in Chennai it was like a hotspot and things like that. So we even made like a UV sterilizer, like a makeshift solution to ensure that everyone was safe and protected. And the best part of being part of the collective is that we were able to learn, design, and experiment, at every stage. Like say for example, we have this all the time active groups, which which was like a living encyclopedia. Like anytime we are stuck, or anyone for that matter, like any lab for that matter, if we are stuck, you go there, you get results instantly, and or maybe answers, right? Like maybe they will like, okay, try this, try that. And also, more importantly, like Richa mentioned, like back then we had a very strict lockdown in Chennai. We couldn't really move out of our own streets. But then, because we were part of the movement, we had the credibility to reach out to the police department and source materials from the shops which were closed. And that gave us a huge boost, because I've spoken to a few labs who were like, expressing kind of challenges that how are we even going to source the materials at the first place. But then this was very, very helpful for us. And we were also financially supported by the funds that they raised, and during at various stages of the prototyping. And more importantly, this is like a Jamboard created by one of the members, and basically we wanted to have like a platform wherein we can share the results, because everyone, like every team was designing different canisters, different designs. So we wanted to have one benchmarking page where we can compare and things like that. So that was super useful. So initially we were using like canisters of like which is used in water purification. It was cool. We thought like, yeah, it makes sense, because we couldn't really source the original PVC canisters as mentioned in the Oxygen design. We used this, but then we had leaks, and we at 2 points we had like one explosion in the filter, and also like the setting of the RO cap, like that broke. So we had to change it to aluminum canisters because we wanted to be safe for the first place. So yeah, and mostly being in a coastal region, again, we had around 80% relative humidity, as I told you, and we were able to reduce it to 11.8% so far. And you can, as you can see here, like we made like a real-time monitoring web app, because once what happened, like we were initially using LabVIEW software, but then LabVIEW required like a cable to be connected, and once I was using my I had kept the Oxygen near my table, and when the explosion happened, it just happened on my face. So that was super dangerous. So I had to kind of switch it to like a web app. Like one of the volunteers developed it for us in Chennai, and then even though PCB was like super cool and very convenient, but then we faced like a lot of issues with very jugaad things like jumper cables, right? So then we made like a hand soldered controller, which is what we're using right now. Yeah, and the version 1 was very simple. So we used like simple 10-inch Oro canisters. We used like 2 of them, 4 of them in series parallel, like different configurations. But then we were not getting much of output. We got like around 45% output. And then we switched to, and then we thought that maybe it's because it's in series and it didn't have enough time to surge and purge. So then we switched to like 20-inch canisters in version 2, which was quite okay. We got around 60%, but still there were air leaks at the cap, which is basically at the outlet of oxygen. So we tried to seal it with silicon gel, but it was not really working because it was at high pressure. Then again, because the canisters, like the Oro canisters, had like plastic threading, so under pressure we always had a fear of what will explode when. Then we had to like switch to aluminum canisters that we fabricated in Chennai. So we are right now in the fine-tuning stage. With the third version, we are now focusing on the embodiment design so that it can be aesthetically and ergonomically contextual to the medical settings. And with the third wave, which has been like notified by government bodies, it's going to be here in a few weeks. So right now we are getting ready to scale up to meet another potential demand, at least locally, like in and around Chennai. So that's what we are trying to do right now. Yeah. So I'll be happy to have some comments. Thank you, guys.
Great. Thank you so much, Krishna. If you could just stop sharing as well, then I'm just going to switch to, just going to switch to gallery mode, and then we can all answer some questions. So great. Thank you, everyone, so much. All the labs, all the members of the collective, everyone's been really working really hard for the last couple of weeks, and it's been almost about 2 months now that we've been doing extremely amazing work across board to really get the things in action, and really excited to really have everyone's be part of this. And it's just been a very beautiful journey for us as well to learn from everyone, and vice versa, I'm guessing. So there are a few questions on the chat which I wanted to sort of take up, and just starting from the bottom, right? So someone's asking us, is it medical grade or just a hobby project? So I want to answer that before anyone else could comment, but Putul, if you think this is a hobby-based project, we all have working businesses, literally all of us who are part of the collective. All of us have day jobs. It's not something that we do. We're not doing for a hobby, but it's more from a perspective of really bringing open innovation to medical equipment as well. Because at the moment, when you think about medical grade equipment, there's a lot of work that large companies do. There's a lot of capex that needs to be put into the whole system. There's a lot of things that happen when you're not sharing a lot of knowledge, and at the end of the day, the access to this becomes restrictive. So the idea of the collective and the initiative is to sort of create an open innovation system so that we can all work collaboratively to bring down the costs, innovate better, faster, cheaper, and in a more agile manner. So that's pretty much what we are trying to do here. So all of us have been working to get this certified. So like I mentioned earlier as well, we have about 2 units which are in engineering certification stage, and we are pushing for certification as well, and that's where we stand. But please feel free, guys, to add to this question if anybody would like to.
Maybe Vijay should add in.
Yeah, Vijay, maybe you want to say something about, is it a hobby project or not?
Sure. I mean, so when it comes down, we've been following the ISO documentation when it comes down to, the features on this machine. When we're even developing and creating this thing, all of this was there. Again, WHO has a document, ISO has a document for oxygen concentrators. And this is what we are using. Again, even the alarms that it needs to have, the display that it needs to have, we're making sure that we are up to spec over there. And once we have the PCB, like from what Vaibhav is doing, again, making sure we have the EMI, EMC also, like the pre-compliance done and the compliance done. So all of these are steps. And one of the reasons, again, sort of we are going back and forth between us and TUV over here in Bangalore is sort of, the first version that we made was, Jugaad and just getting it together and making sure that, we are figuring out how to make an oxygen concentrator to begin with. I mean, you don't get everything up and running, in the first prototype that you make. But in the subsequent ones, you iterate and keep fixing it. You make sure that you have an entire checklist of things that you need to get done. And ultimately, the goal is to meet all of those items that a medical grade oxygen concentrator requires and get to market. And I think Richa put it brilliantly. We all have working businesses, and we want to use that experience in terms of not only like as makers, but also as people who are in, have startups on their own to scale this and actually contribute to society and actually manufacture this. And there are a lot more labs that who are in the collective who are actually like, fabricators and established businesses who have the capability of scaling this up, but do not necessarily have the capability of doing the R&D. And by coming together, not only in terms of, expertise sharing, but also in terms of business side, everybody has one piece of the puzzle to come together. I think, Richa put it brilliantly when it comes down to, large companies and corporates require a lot of work, lot of manpower, a lot of resources to get something like this done. But with open innovation, I've seen it firsthand. Again, it's been amazing what you've done in the last 45 days. And we're almost there when it comes down to getting this productized.
Awesome. Great. So I'm going to now do the next set of questions. Somebody is asking us, sorry, what's the plan for display integration? Can we integrate the display? I think we've already done that, right?
Yes, we are. The system will have a display for sure.
Yeah, I think even in Vijay's system and a few other systems, there is already a display.
Yep, the system display is going to be part of the system. It's already integrated, and as part of Vivian's new board as well, there's going to be a display that's going to add to it.
Yeah, so let me say one thing. As mentioned, the display, it will be easy through the connection on the board directly to a display that will be testing, or through the 30-pin breakout of the ESP chip. So let's say if someone can't purchase or can't get the display, and that will be directly connected to the board, then he can choose, whatever pins that will suit the display and will go on with it.
Okay, great. So that's on the display. I want to also take up this question. So somebody's talking about the fact that we didn't find, they are with Vatsal Patel, they are also making oxygen concentrators for 5 to 10 liters per minute kind of LPM. But they say that we didn't find much change in percentage with lithium or sodium-based zeolite from AGC Chemicals Geelong. Do we have any reference of if we've used AGC and has there been an issue with their zeolites? Any?
Okay, so there could be many different issues. If you look at the system, the timings, the pressures. So maybe an offline discussion on this would be better with them.
So they haven't seen any difference. So in the sense that it's working. So is it working for them for both sodium and lithium? Is that the question? Or it's not working on both?
So they're saying that they're maximum getting 91% with no change with lithium. Okay, so then maybe there could be some.
Maybe we take that offline.
Yeah, maybe Vatsal, if you could reach out to us, you could come in for our design and feedback calls that we do every Mondays and Thursdays as part of the collective, where we are doing individual feedbacks on specific, devices. And the collective is pretty open in terms of sort of understanding specific issues. So if anybody would like to join those, please head to the website. I've shared the link on the chat. And there's a button called Join the M19 Collective, and we'll add you to the Telegram groups, etc., so that you can also present your, devices and take help largely on problem solving for specific, parts of your fine tuning or anything else that you need. Okay, a couple of quick questions. We'd already asked. Have you received practical experience? Theoretically, everyone is saying, but is there any test for testing sodium-based or lithium-based zeolite? Do we know something about that? Gorba, Vijay, Krishna, anyone?
I don't know. You have to go by the data sheet.
Yeah, we're really going by the data sheet of these manufacturers where, that's how we get to know about the lithium and the sodium-based zeolite, I guess, for now. Another one, loud noise may not be optimal for a patient. What are we trying to do about that?
Yeah, so on that note, we're going to be obviously using dampeners. So that's one of the reasons why we've separated out the compressor unit in our system so that we can isolate the sound in that system as much as possible to reduce the sound.
Yeah. Sound damping is part of the problem that we're working on for sure.
Sound dampening is definitely one of the problems that we're working on. And once we enclose the system, in the next couple of days, we'll be able to test that and see. Currently, we're about at 70 decibels within a meter range. Obviously, on the microphone, it's more amplified, but 70 decibels if you're standing about 1 meter from the device. We're trying to bring it down to about 60, 65.
That 70 is a completely open system, right?
Yeah, 70 is with a completely open system.
Okay.
Vijay made any tests at his
Vijay, have you made any tests on your side on your device? What decibels are you at?
Mine is slightly more, mine is 78, 75, 78. But again, we've opened up a few oxygen concentrators. They have foam lining on the inside. This is probably what we're going to do at the end. And also, again, since we're using sodium 13X, we need a much larger compressor, which probably we will not need when we are switching over to Lithium X. So that is sort of the next thing. So make the compressor smaller, line the insides with foam. That is what your commercial oxygen concentrator use. And again, so more or less we're learning also from what the Chinese are doing, opening up. So it's not just their closed box, but also seeing what other concentrators that are already there in the market are using.
Okay, thanks. Another question from Sheshan Babu is, can't Peltier system do a better job? Anybody has any insights on that?
Expensive. And yeah, I mean, power-wise too expensive, cost-wise also too expensive. Needs a lot of watts and needs a lot of money.
Sure. Okay, that's, I mean, of course, in an Indian...
Also not easy.
Peltier, I think Vijay, this one is a little, this one. Peltier, we have tried Peltier-based cooling. It does work, but the efficiency when it comes to the power and the additional cooling required for the Peltier itself is much higher. So the cost is not efficient on that as well.
Yeah, I mean, obviously, India is a very price-sensitive market. So, I mean, at the end of the day, it is the cost-benefit analysis for most hospitals. They don't have budgets. So a lot of things need to be checked. And I think the PSA system does a better job on at least, bringing down the cost, I believe. So I guess that's the answer on that. Another question is, do you really believe Arduino is really fit to be used in medical automation?
Yeah. I guess we already answered that question, but when we talk about Arduino, it's a platform, but most probably they thought about AVR chips, same as other chips. It is already used in many medical equipment, so it's not a new thing. And then we can see equipment from the 90s, from the 80s, still working till now with microprocessors. There is no problem with that. Our application doesn't require like FPGAs or like very sophisticated chips. It doesn't require all of that, or like an expensive chip. The chips we're using is much more like it's more than enough for our application.
And I also would like to add on to Mohammed's this one there. See, the code that we are developing for the new board is on VS Code with the platform IO base. So it's a little more professional, and it will be more compact. The code itself will be more compact because we are doing a little bit of assembly coding as well onto that.
Okay, great. Thanks, guys, for that. Couple more questions, last few questions that I want to take in, which we've not answered yet. So in general, just to give everyone the overview, we are trying to make concentrators in most of our labs, which are at least about 15 liters per minute, right? That's what we all are aiming for, because they can be used in ICU and high-risk settings for, more critical patients. while the ones that you get on the market, which are sort of easily available outside, which is between up to 10 liters per minute, might not be possibly used in ICUs. So we are trying to really get to that point where it can be used in hospitals as well.
So going up and down on the LPM in terms of 10 to 15 or 15 to 20 or 5 to 10, it's pretty much a matter of the sieve and the compressor.
Scaling up the whole thing.
So it's at the end of the day, once you've figured out how the system works, then it's just about scaling up the sieves and scaling up your compressor as an input to how much pressure you're actually putting into the system to be able to get out the right amount of LPM at the end and the right amount of sieve volume in terms of the zeolite volume that you're exposing it to. So once you've figured out 5 LPM, it's relatively straightforward to go higher, but once you've definitely reached out 15 to 20 LPM, it's pretty straightforward to go lower.
Yeah.
Much easier to go lower once you've been able to definitely figure out the 15 to 20.
Yeah, a couple of questions. Thanks. A couple of questions around certification. Actually, maybe I'm going to pass that to Vijay and add more to it as well. Vijay, you want to give them a basic brief on what we understand about certification at the moment?
Sure. So there's several different ways of doing this. One is, again, DRDO has set up a certification for using their design. They also have certain specifications too. So that is one. Then TUV, when it comes down to doing any medical device, has to go through. You have the EMI, EMC, and then there is ISO certification for oxygen concentrators. This is mostly what, if you go into a body like TUV or UL to certify your machine, this is what they will be following. Parallelly, I think Richa also mentioned this. A lot of the oxygen concentrators that are already in the market are just for recreational use, but that is what they're using. They do not, most of them at least, again, there are exceptions to that, but most of them do not come with any sort of certification to begin with. But with the approval of a hospital's ethical committee, they are being used on patients. So that's sort of a brief overview about certification. But again, because of the situation, there are sort of systems of fast track certification. I mean, I'll tell you one of the things that even we faced, right? So we were looking at, okay, something to get fast. We talked to a hospital to I'm not going to name the hospital, but we were basically asking if they can certify the machine and to see if it works. Ultimately, what they got back to us saying that, hey, we will actually hook it up to a patient and see if the SpO2 value goes up or down. So that is a situation that is there on the field right now when it comes down to using these machines. What we are finding out that oxygen concentrators have never been manufactured in India, or at least there are no certification within India. So the entire government is sort of warming up to this, and they have several certification bodies like DRDO. They are the drug controller of India that is issuing certification again, but based on certain specifications that they are putting out.
Yeah, just to add to Vijay, and what at least I have understood in the last year of sort of understanding certifications is that one, of course, the ethical committee, because it's a non-invasive device, can take a call if they want to sort of use it, as long as it has specific things like the output is being shown, or there's an alarm when it's below, say, 90% your oxygen levels. The WHO specifies all these basic things that you need to do. The government of India also had a circular which said that these are specific things that you need in your concentrator, as long as there's a display, as long as that there's an alarm whenever the LPM or the concentration level goes down, so that the user at the hospital using it has an indication of it. It's possibly good to go. The BIS has an open consultation which I think closes this June around how to standardize and regulate oxygen concentrators and things like that. But it's an open consultation for now, so they will get into sort of more deeper discussions around how to take that consultation forward in terms of regulatory changes that need to be made, etc. In addition to that, what we also do understand is a lot of concentrators that are coming in from different parts of the world are not really medical grade concentrators as well, but can be effectively used because some of them are recreational, but work fine, up to 10 liters per minute and all of that. But having FDA approval or NIOSH standard kind of approvals like in the United States, we don't have a body like that, or we don't have certification labs like that that can run those kind of tests in India at the moment, because it was never manufactured here. So obviously this has happened with multiple COVID related products in the last year as well, where people have gone into the whole cycle of certification and never really got beyond and past that, and the situation has gotten beyond that, right? So I think there has been coordination with the regulatory bodies, but again, it also depends on a lot of inways into these regulatory bodies, knowing somebody, etc. There are channels that have opened up now, but we are trying to do the NABL certification, which is an engineering certification for the device, so that at least we know from a durability standpoint it does not have any issues, so that we can go ahead and give it out. So that's where we stand in certification, if anybody had those questions around that. Okay, last compressor overheating problem. Somebody's asked for that.
We need lots of cooling for sure. We can show you here. Is your phone?
Yeah, we can show you here. One second.
But yeah, Vijay system, he's got lots of fans.
Yeah, so I mean,
Yeah, he's got a
so
massive.
I've got a lot of fans. I have 2 over here, then I have a massive one at the back, if you can see. These are all basically exhaust fans that we've got. This is the only thing that we could find with proper CFM that could cool something as big as this. So when it comes down to heating, the few things that I've understood is these compressors are actually rated for about 85-90 degrees of working temperature, and if it goes above that, it does have an internal shut off, so it does sort of like turn off itself so it doesn't kill itself. So definitely it's an important thing to consider, but most of these medical grade compressors already have like protection against overheating.
Yeah. So yeah, there of course need for a lot of fans and all that kind of stuff. It is an issue, especially with the 2 HP compressors that we're using. They might get overheated, but on that, the chiller system is something that we've been working on, and Vaibhav's just trying to admit over here. So
Yep.
yeah, are you guys taking them through the chiller?
Yeah.
Yeah, okay.
Okay. Okay, so here we are. And what you can see over here is
So this one is 1.8 kilowatts, 2.5 horsepower compressor. We've got 2 cooling fans here.
and 2 at the back.
High flow, these are high flow capacity. There's another 2 here at the bottom. Plus, we will eventually hook up a chiller system, which will actually pump in cold air into the heads of the compressor. So we have noticed some better performance with that. The compressor heats up a bit less. It runs much cooler. The tubes don't get heated up and so on. So I think there is some merit to that approach. Right now, it's still work in progress. But yeah, using a chiller and using cooling fans is how we're going to tackle the temperature problem.
Yeah, there's a significant drop in the output of the temperature, the air coming out of the compressor. When you chill the air before, literally goes down to at least 20 degrees lesser. And also, obviously, it takes off all the humidity. And that's what we're doing over here with this unit. Yep. Ambient air is going in, getting condensed. All the water pretty much falls down. And we take the air from the back into our system.
Yeah. It's a huge issue for sure.
Okay, great. Thanks, guys. So I think with that, we come to an end of this webinar. We had a bit of a technical issue in the beginning, so really sorry about that. But hopefully we'll be able to do this again with a much larger group, and hopefully we can, get our technical systems in place before we do it the next time. But thank you so much, everyone, for joining. I think this will also be recorded on the YouTube channel. If you want to get more details about the initiative, what we are up to, we are all active on all our social media. And if you would want to sort of help accelerate open innovation, you can also go and donate to the campaign so that we can keep doing what we are doing. And hopefully the third wave that is anticipated in the next couple of weeks, we are able to contribute even more better as part of the collective. So thank you so much, everyone, for joining. And thanks all the labs and the members for taking out time on a Sunday to do this. So see you, everyone. And we'll be in touch. And for anything, please reach out to us. We are all available. And all the information is on our website, on Makers Asylum. And would be happy to connect and also, support anyone who's working on specific problem statements, and all of us will be happy to contribute and give feedback. Thank you so much.
Thank you.
All right, so. I'm going to end this session so that I can stop the stream, I guess. So thank you guys for joining. Sorry for all the confusion. And hopefully, anyways, we'll be in touch this week. So for